Okay, so let's continue the discussion on group actions. So let us start with this. So let G be a group and let A be a set. Clear? Let G be a group and let A be a set. Let me write this with some other color. I guess this will do. Let G be a group and let A be a set. We know what this means, right? G acting on A. G acting on A. This basically means that there is a there is a mapping from G cross A to A, right? And this mapping, suppose it sends G and small a to GA, it needs to satisfy certain conditions. The first condition being that G1, G2 on A, this is nothing but G1 on G2 on A, right? And number two is that 1 when acts on A, it gives A back. These are the conditions we require to define a group action, right? Now what we do is we define a group action on A. Okay. So let sorry yeah let let G act on A. Clear? Let G act on A. So what we do is we define an equivalence relation on A. Okay, we define a relation on A such that A is related to B if and only if A can be written as G acting on B for some G in G. Okay. This term we will be simply saying this to be GB. Okay. So this is an equivalence relation. Okay, and that is very easy to check because you can write any element in the form 1 times that, right? This is pretty trivial because that's the exact property of a group action. Number two, if you have A in the form of this, right? So you can just pre-multiply with G inverse, let's say. So if you do this, so G inverse acting on A is nothing but G inverse G acting on B, right? Because you can associate G inverse and G like this. This is nothing but B. So since G inverse is also an element from capital G, therefore A is, so this means B is related to A, right? And transitive property also holds directly from this property. So that's pretty easy to notice. So therefore, this is an equivalence class. This is an equivalence class, sorry, equivalence relation. And we know that equivalence relations have a very unique property. Have two, rather I would say, yeah, have one unique property that it partitions the set on which the relation is defined into equivalence classes, right? So A can be written as the equivalence classes of the elements small a, their unions, right? That small a is in capital. Okay, and this is possible. The reason is being, first of all, you can express this as a union, and it is a disjoint union because equivalence classes are either the same or are disjoint. So if the equivalence class of A and the equivalence class of B is non-empty, then that happens if and only if they are equal. Clear? Or rather, I should not use this term, if and only if. That's a very bad mathematical procedure. Right? Yeah, this will do. Correct? Okay. Um. So now our claim is that our claim. So in the previous class, we had defined what the stabilizer of a group action is, right? Right. In the previous lecture, we had a discussion about what the stabilizer of an element small a in the set capital A is the collection of all those elements in the group G which fixes A, right? So if I just recall, so the stabilizer of A is defined to be the set of all those elements G in capital G such that G fixes A, right? And you can also check that the stabilizer is a subgroup of G. Clear? Now, so let me just write it as a proposition. As a proposition. Let me just write it as a proposition. So the proposition is basically that the number of elements in the equivalence class of A with respect to obviously this relation we just defined is same as the index of the stabilizer of A. Rather, I should write it like this. Yeah. So if you remember what the index of the stabilizer basically means, so basically suppose, if you had studied Lagrange's theorem, I think we have covered this in the first lecture where we had discussed general group theory. So it's like, so if you have a subgroup H of G, then G, the cardinality of G can be represented as K times the cardinality of H. And K is basically, so it represents the number of left cosets of H, number of distinct left cosets of H in G, right? And we represent this K as the index of H in G. So index of the stabilizer GA in G basically means what are the number of possible distinct left cosets of GA in G. Okay, let's start to prove this. Okay, let's prove this. Okay. What we do is we define a bijection between the left cosets of GA in G and the elements of the in the equivalence class which contains A. Obviously, an equivalence class which contains A must be same as the equivalence class of A, right? Because if A is in the equivalence class of B, for example, and A is also in the equivalence class of itself, because obviously A is related to 1, then, sorry, A is obviously related to itself, then A intersection B is non-empty, right? But that implies both must be identical, right? So let us come up with the proof. So what we do is we define a bijection from the left cosets of GA to the elements of the equivalence class in A. So how do we do that basically? So let CA be the equivalence class of A. Okay. Then CA basically consists of the elements of the form GA, right? Such that G is in G. This is direct from the definition of an equivalence class. Now suppose B is an element from CA. Okay. Then obviously there exists some G in G such that B can be written as GA, right? Now GGA is a left coset of GA in G. Therefore define B which can be written as GA. So define the mapping which sends B which can be written as GA to GGA. Clear? Clear? So this is obviously a mapping from CA to the set of all left cosets of GGA. Clear? Set of all left cosets of GA in G. Okay. Now this map is surjective by definition because for every element, for every left coset small g GA, you can have an element small g such that G can be acting on A, or you can consider the element GA, and if we represent that element as B, then B is surely from CA, right? So it's obviously surjective. And this is also a 1-1 because if you consider the equality, say small g GA is equals to small h GA, Now from the properties of left cosets, this basically represents that GH inverse is in GA, right? But what does GA basically mean? So it fixes A, right? So that means GH inverse. So basically that means GH inverse of A. So it fixes A, right? Right? Yeah. But sorry, have I done any mistake here? No, I guess yeah, correct. But what does this mean? So this means G on A is same as H on A, right? And this is an if and only if condition as well. Then obviously check it. Okay, clear. Got it. Okay. So what does this mean? So this basically means that, or I should write it like this. Yeah, this is a mistake. Wait a minute. Let me write it like this because I have changed the order of the elements G and H, and I can't do that because I have nowhere mentioned that the group is abelian. Okay. So let me do it like this. So if this happens, if I pre-multiply by H inverse, yeah, correct. So this is H inverse G is in GA, correct. But that implies G inverse G of A. I should not use this. So that means H inverse G on A is equals to A. But that means G on A is same as H on A. Yeah. So this is obviously 1 1. Correct? Therefore, there's a bijection. Now, if there is a bijection, so the elements in CA will be same as the elements in, so number of elements, or rather I can directly say a number of left cosets of GA in G. Number of distinct left cosets. Because as we are speaking about a set of all left cosets, so obviously there is no repetition inside, right? But number of left cosets of G in GA in G is nothing but the index of GA in G. Okay, clear? Now the important things to observe here is that, or rather I should give a definition first. So this equivalence class, right? So if A is an element from capital A, then this equivalence class of A with respect to the relation we defined, which is set of all the elements of the form GOA such that G is in A, sorry, G is in G. Now this is a subset of A, obviously. So is called the orbit of A. Is called the orbit of A. Clear? And we will often use the notation OA. Clear? Now notice one thing. So the cardinality of CA is nothing but the cardinality of OA because they are the same. We are just using a different notation. So we have found that the cardinality of OA is nothing but the index of GA in G. But from Lagrange's theorem, you should observe that the index of GA in G is nothing but the index of G upon index of, sorry, the cardinality of G upon the cardinality of GA. So if I simply cross multiply, I will get the cardinality of G. Now obviously the cardinality of GA is at least 1, right? It cannot be 0 because 1 will fix every element. So 1 is obviously in this stabilizer, right? So G can be written as the orbit of A times the orbit of GA. And this is called the orbit stabilizer counting theorem as far as I remember. This is called the orbit stabilizer counting theorem. There are a number of counting theorems in group theory. Counting theorems in the sense the theorems which help us to find out the cardinality of a certain group. So this is one of the counting theorems. And since it involves the orbits and the stabilizers of a certain group action, so we obviously name it the orbit stabilizer counting theorem. One more very important and very highly used counting theorem is the class equation. I'll try to get into that in this lecture itself. Okay. Yeah. So let us first define a few important terminologies related to group theory. So which are the centers, centralizers, and the normalizers. So definition. So we denote it as CGA. Okay. So CGA is the set of all elements small g in capital G such that G small a G inverse is equals to A for all A in A. Okay. Where A is a subset of G and G is a group and G is a group. Okay. This set CGA is called the centralizer, the centralizer of A in G. So what does this set basically contain? So this set basically contains all those elements in the group which commutes with every element in this subset A. Clear? Now if A is the singleton set small a, then the centralizer of capital A is usually denoted as the centralizer of this element A, because this is utterly obvious, right? Further, notice that if capital A is the singleton set A, then all integral powers of A will be in the centralizer of small a, right? Because the properties of exponents will help us commute every integral power of A with A. Yeah. And this happens for all n in C. Clear? Observe, or rather I should write it as a say proposition. Proposition. The centralizer of a certain set in G is a subgroup. Okay. Centralizer of the set A is a subgroup of G. Clear? So let's try to prove this. Yeah, let's do it. So to prove that it's a subgroup of G, now this is utterly obvious that the centralizer is a subset of G, which is exactly from its definition, right? Therefore, associativity holds trivially in this, right? Associativity holds trivially in this, and if G is commutative, then that commutativity also holds trivially in this. So what we exactly need to prove is that it's closed under the operation induced on G, or sorry, the operation which G consists of, and it is closed in the case of inverses, right? That will do. So suppose let's say suppose small a is in CGA. So what does that imply? So that implies that I should not use the term A. Let G is in small is in CGA. So that implies G small a G inverse is equals to A for all A in A, right? So if I pre-multiply by G inverse, let's say, so I will get A G inverse is equals to G inverse A. This also happens for all A in A. And then if I again so now if I post multiply by G, that is if I write multiply by G, then I'll get A is equals to G inverse A G for all A in A. But this is same as G inverse A G inverse whole inverse, right? For all A in A. So that means G inverse is in capital G. Sorry, is in the centralizer of A. So it's closed under inverses. If I consists of two, if I consider two elements, let's say G1 and G2 are in the centralizer of A. So I need to show that G1, G2, A, G1, G2 inverse is equal to A. So this is our claim, right? This is our claim. So how do we prove this? Now observe that G1, G2, A, G1, G2 inverse. So this is basically G1, G2, A, G2 inverse, G1 inverse. Because G1, G2 inverse is G2 inverse, G1 inverse, right? Now this is A. So this is equals to G1, A, G2 inverse as, sorry, G1, A, G1 inverse as G2 is in the centralizer. So it fixes A. I mean, this conjugates fixes A, right? But this is again A, because G1 is also in the centralizer. right? Therefore, G1, G2 is also in CGA. Therefore, CGA is a subgroup of G. Clear? Okay. Okay. Yeah. See, if I consider a definition, or rather, I should say, if I consider an example. So, you people have the concept of a quaternion group, right? So, it consists of the elements plus minus 1, plus minus I, plus minus j, and plus minus k, right? The important property of this group is that every subgroup of Q8 is cyclic, but Q8 itself is not. Or you can say every subgroup of Q8 is abelian, but Q8 is not. The subgroups of Q8 are of the form. So you have the subgroup uh, generated by I, generated by J, generated by K, generated by and the one minus one. Yeah, got it. And this is obviously in every other subgroup as well, right? Now my claim is that, or rather I should say, this is pretty trivial to know that the centralizer of the element I, this is nothing but plus minus 1 and plus minus I. Now, why is this obvious? Because if you know the structure of Q8, then you should know what happens is basically, so you have I, you have J, you have K, let's say. So Ij gives you K, Ji gives you minus K. So J doesn't commute with I. Similarly, Ki gives you J, but Ik gives you minus J. So K even does not commute with I. So obviously, the now I will obviously commute with itself because I squared is 1. So the other properties of I, J and K are their squares are 1. So they are all of order 2. So I squared is 1, J squared is 1 and K squared is 1 as well. So I commutes with itself and plus 1 and minus 1 also commute with I, which is very trivial to notice. Clear? Okay, so let us move to the next definition. So let me define the center of a group. Okay, so the ZG, we denote it as ZG. So ZG is defined as all those elements small g in capital G such that GA is equals to AG for all G in G. Clear? For all A in G. Sorry, for all A in G. Or rather, let me use a different notation because I have already used the element A for denoting the elements in the subset A, right? So let's GX for all X in G. Clear? Now, obviously, from this definition, we can find that ZG, that is, so this is called the center of G. ZG is called the center of G. So this contains every element which, so this consists of all those elements which commute with every element in G. So by definition itself, ZG must be a subset of the centralizer of the subset A for all subsets, right? Now if A is equals to G, then ZG is equals to the centralizer of A in G, right? If A equal to G. But we know this is a subgroup of capital G. So that means ZG is also a subgroup of capital G. So if ZG is a subgroup of capital G and ZG is contained in CGA, therefore obviously ZG is also a subgroup of CGA. That's pretty obvious to us. Clear? Got it? We can obviously directly prove that the center is a subgroup of G by the same steps which we had, kind of the same steps which we had used to prove that the centralizer of a subset A in G is a subgroup of G. Clear? So the next definition. Okay. Suppose A is a subset of G. G is a group. We define the set GAG inverse as collection of all the elements of the form G small a G inverse such that small a is in capital. Then we define the normalizer of the set A in G. Now obviously centralizer was defined for an element, ZG was defined in general for a group, and normalizers are defined for sets. Okay. So we say normalizer of a set A in G is the collection of all those elements in G which are denoted by small g, such that G capital A G inverse is same as. Okay. So what is happening basically? So in case of a centralizer, we are counting those elements which commute with the elements in capital A. In case of a normalizer, we are collecting those elements which commute with the whole set A. Clear? Clear? Because G capital A G inverse equal to A, this doesn't necessarily imply that G small a is equals to A G for all A in A. Because this implies that there exists some A1 in capital A such that G A G inverse is equals to A1. So this A1 and A are not necessarily same. Okay, so they are not identical. But obviously, the centralizer of the subset A, this must be a subgroup of the normalizer, which is again evident from the definition. A centralizer is a subgroup of this. Yeah, correct. Because if an element commutes with every single element of A, then obviously it will commute with the whole set. Right? That is, if I choose an element from centralizer of A, then that means this happens. So, yeah, right. So if I choose an element from the centralizer of S a small a, so that means G inverse is equals to A for all A in A. But that obviously necessarily means so G capital A G inverse is equals to, right? So G must be in the normalizer of A as well. And the converse is obviously not true by just the way I just explained. Okay, so let us go through a few examples. Example number 1. Suppose G is the dihedral group of regular four-sided polygon. Okay, so we also represent this as D4, right? So what are the elements in D8? So they are 1, R squared, R cubed. Then we have S, SR, SR squared, SR cubed, where R represents rotations and S represents reflections. Clear? I might be bringing out a separate lecture to explain how this dihedral group is constructed. Okay, that is pretty a kind of a complicated conceptual part, but we will do it. No worries. Yeah. So rotations in the sense, if I simply explain, suppose you have a square like this. So 1, 2, 3, 4. So rotations means basically you are sending 1 to 2. One single rotation I am talking about, that is R. Okay, if I speak about just R, so what does R basically mean? So R is that element, that rotation which sends 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So if you compose R with R, so 1 is sent to 3, right? So 1 is then sent to 3 by R squared, 3 is sent to 1 by R squared, 2 is sent to 4 by R squared, and 4 is sent to 2 by R squared. Similarly, R cubed is 1 is sent to 4 by R cubed. So you are doing the rotation thrice. Reflections are basically, so if I talk about the reflections, say, so what are the possible reflections basically? So you can reflect over this, over this, over this, and over this. So these are the 4 reflections, right? Yeah, so we have these 4 reflections, correct? Okay. So my first question is that what is the center of this G? There is a very important property here, which is RS is equals to SR inverse. SR inverse, right? So if you imply this property and check out through the elements in D8, you will obviously get that the center of G, that is the only elements which commute with every element of D8, R1, which is very obvious, and R squared. Okay, you can check this. This is pretty because this is a very short set, right? You can do it obviously. If I consider A to be the subgroup 1 R squared R cubed. So this is obviously a subgroup, right? Because this is nothing but the cyclic group generated by R. R has order 4, right? R to the power 4 is 1. So this part is a subgroup of G, right? This is a subgroup. So what is the centralizer of this subgroup? What are the elements which commute with them? Obviously S won't. Obviously S won't because of this relation directly. So what are the elements? So we know that a cyclic group is abelian, right? So if a cyclic group is abelian, then every element in A will commute with every element in A. Obviously, so A is obviously there, right? So every element 1 R squared and R cubed are obviously in the centralizer. But is there a way? Is any other element possible? It is obviously not because of this relation, right? So the centralizer must be A itself. Clear? Normalizer of A is the whole set. Normalizer of A is the whole set, and I'll give it as an exercise. This will help you understand the how the normalizer works. Just go direct by definition. There is nothing else. Directly go by definition. Okay. One more thing to observe about centers is that um, if G is abelian, let's say, if G is abelian, then the center of G is the whole of G, right? Because every element in G will commute with every element in G because G is abelian. Centralizer of centralizer of any subset A must be same as normalizer of any subset A. Because in this case, GA G inverse equal to A, this will obviously imply GA G inverse equal to A, equal to small a. Because you can commute A and G inverse. So if you commute A and G inverse, so G and G inverse gives you 1, so this must be equal to A, right? Because this is equals to G inverse, which is equals to A. Right, so that means A must be in the centralizer as well. But we had previously proved that the centralizer is contained in the normalizer. This set of statements gives the normalizer is contained in the centralizer. So therefore they are same. And they must be same to G as well, right? Because every element commutes in G because G is abelian. Yeah. Let us consider the next example. Suppose I consider G to be the set S3, right? S3 is the set of all permutations of the elements 1, 2, and 3. Okay. What are the elements if I specifically write? So this is the element 1, which is the identity, obviously. Identity mapping, which sends 1 to 1, 2 to 2, and 3 to 3. Then you can send 1 to 2 and 2 back to 1. You can send 1 to 3 and 3 back to 1. You can send 2 to 3 and 3 back to 2. You can send 1 to 2, 2 to 3, and 3 back to 1. And you can send 1 to 3, 3 to 2, and 2 back to 1. Right? This is the cyclic notation. The cyclic notation basically, so if you have this cyclic notation, say I1, I2, I3, so until Ik in a permutation set, permutation group, then this typically means the permutation which has I1 going to I2, I2 going to I3, and so on. Ik minus 1 goes to Ik, and Ik goes to I1. Clear? So these are the exact elements. Now notice that if this set you have A1 and the element 1, 2, then this is a subgroup of G. This is a subgroup of G. Okay. Now obviously notice that every element commutes with its power, right? Every element commutes with its powers. So A is obviously a subgroup of the centralizer of A. Clear? And we can use the notation of being a subgroup because A is a subgroup of G and A is contained in the centralizer, so obviously it must be a subgroup, right? Now, so that implies the cardinality of A, or rather I should use it on the order. So order of A divides the order of the centralizer. And this is from the Lagrange's theorem. This is from the Lagrange's theorem. Now what is the order of A? So order of A is 2, right? And what is the possible order of centralizer of A? So it can be either 2 or it can be 6, right? Because 2 divides it. So that implies the order of the centralizer can be equal to 2 or 6, right? Clear? But if it is 6, if 6, then the centralizer must be equal to the whole group S3, right? Right? But now see why I have not written here the option of 4, because if the order of G is 6, then obviously G cannot have a subgroup of order 4, right? Because 4 doesn't divide 6. So the only possible subgroups are of order 2, 3 and 6. 1, 2, 3 and 6, because these are the only factors of 6. So and 2 divides only 2 and 6, right? So that is the thing. So the centralizer of A becomes S3 if its order is 6. But so what does that mean? So that means that A must be contained in the center. A must be contained in the center, right? No, because if the centralizer becomes equal to S3, so the obviously A must be inside the center of G as well, right? But what does that? But 1, 2 and 1, 2, 3 is not equal to 1, 2, 3, 1, 2, right? So what I actually mean to say is that the element 1, 2 doesn't commute with 1, 2, 3. So that means this is not possible. Every element of A does not commute with every element of S3, right? So therefore a contradiction, right? Therefore a contradiction. That means the order of the centralizer cannot be 6. Therefore the order of the centralizer must be equal to 2. But that is same as the order of A. And we have shown that order of that A is contained in the centralizer. So this obviously means that the centralizer of A must be equal to. Clear? What can we say about the normalizer of A? See, normalizer of A, right? So normalizer of A, then if I pick an element from it, if I pick an element from the normalizer of A, right? So this is inside. So if and only if, so this happens if and only if, sigma 1 sigma inverse equal to 1 and sigma 1 2 sigma inverse is equals to 1, right? The first one is utterly obvious because sigma 1 sigma inverse is nothing but sigma sigma inverse, that's equal to 1. So this happens if and only if sigma 1 2 sigma inverse is equals to 1, right? But this happens if and only if sigma is in the centralizer of it. Now centralizer of A is equal to A, right? Centralizer of A is equal to A. So this means the normalizer is equal to A, right? Now what is the center of S3? See, we know that this is a subgroup of CS3. Yeah, the centralizer of A. Centralizer of A has only 2 elements. So the only possible elements in the center are 1 and 1, 2. But previously we just showed that 1, 2 doesn't commute with the element 1, 2, 3. Therefore 1, 2, 1, the element 1, 2 cannot be in the center. So that means the center is only identity. Clear? Got it. Okay. Now let us study a very important example, or rather I should say a very important group action directly. Okay. So let G be acting on itself. Okay. This is called action on itself. Action on itself. So what is this? So G is acting on a set A where A is nothing but itself. A is G. Clear? So this action is such that G acting on A is by GAG inverse. Clear? For all small g in capital G and small a in capital. Got it? This is obviously a well-defined group action, right? Right? Because if you have G1, G2 on A, then this is nothing but G1, G2, A G2 inverse, G1 inverse. Then you can associate it as G1, G2A, G2 inverse, G1 inverse. But G2A, G2 inverse is G2 acting on A and G1 is acting on the whole. So this is G1 acting on G2 acting on A, right? And 1 acting on A is 1A, 1 inverse, so that is equals to A. So this group action. Previously, notice that we had defined the concept of what a conjugate is. So if I recall, two elements, two elements A and B in G are said to be conjugates if there exists some small element small g in capital G such that G B G inverse is equals to A. Okay. Now A is a conjugate of B is same as saying B is a conjugate of A, because this implies B can be written as G inverse A G, and this is nothing but G inverse A G inverse O inverse, right? And G inverse is in G. Therefore A is related to B implies B is related to A. Now if you recall how the no what was the term? Yeah. So how the orbit of A is defined, right? So orbit of an element A. So this was defined as the set of elements G acting on A such that G is in capital G. So that is same as the number of elements G small a G inverse such that G is in capital G. So this orbit we call it as the conjugacy class, of A, as the conjugacy class of A. Clear? Now a few observations if I make. So observation 1, that is a singleton set A. So this is a conjugacy class of A if and only if GA G inverse equal to A. So that means that is if and only if GA is equal to AG. That means G commutes with A, right? So this is if and only if A is in center of G, right? So if you choose an element from the center of G, then the conjugacy class of that element is the singleton set of that element only. Clear? Okay. Furthermore, notice that if G is abelian, then ZG is the whole of G. Then this very statement is true for all the elements G. Then the orbit of any element A is obviously the singleton set. That is the conjugacy class of any element A in G is the singleton set. I'm not writing that as a point here, because that is very easy to notice if G is abelian. Right? Now, as we defined the conjugacy of two elements, we can also define the conjugacy of two sets, because the elements of the form G capital A G inverse is well defined as we did in the case of a normalizer, right? So definition: two subsets S and T of G are said to be conjugates in G if there exists some element small g in capital G such that T can be written as GSG. Clear? Clear. So what is so if you define this, then what is the stabilizer of the whole set capital S? So it is the set of elements small g in capital G such that G capital S G inverse is nothing but capital S itself, right? But if you recall the definition normalizer, this is nothing but the normalizer of S, right? This is nothing but the normalizer of S in G. Clear? Now, there are very important propositions related to this action which are highly important. Okay, so we go to that. There is one more very important group action, which is the action of a group on itself by left multiplication, or which is called the left regular action of a group G on itself. That gives us also a very important theorem, which is called the Cayley's theorem. So the Cayley's theorem basically says that if you take any subgroup, if you take any group, then you can visualize or identify the group as a subgroup of the symmetric group. Rather, if I speak about only finite groups, because that is more more easy to understand, more simple to visualize. If you take any group G which is finite, let's say, which is finite, then you can identify this as a subgroup of a symmetric group. Let's say Sn. Okay. Now we know that the subgroups of a symmetric group are called the permutation groups, right? So every finite group G, I'm specifically speaking of finite groups. So every finite group G can be identified as a permutation group. Right? That's the Cayley's theorem. So this theorem is pretty historically important, because when these sort of concepts came into existence, then every group was certainly studied as a permutation group. Okay. In the modern approach, we don't do that, because sometimes when the symmetric group is very large, then studying the permutation groups is very complex. So in modern approach, we don't do that, but in the historical approach, every groups were studied as permutation groups itself, right? So let us come to the first proposition. I don't think I will be able to introduce this left regular action of a group G on itself in this lecture, because it's already 46 minutes long and I still have a lot to discuss, but we will surely try to do it in the next part. The proposition that the number of conjugates of a subset S in a group G is the index of S, that is this, correct? In particular, the number of conjugates of an element S of G is equal to the index of the centralizer of that element. Now the proof is fairly simple, because during the start of this lecture we had defined the concept of the orbit, right? Where we had proved that the set of elements in the, just the color, we proved that the set of elements in the equivalence class is same as the index of the stabilizer of that class, right? Now, and this was exactly the orbit of it. So if I consider the concept of conjugate of a set, then what is the orbit of that? The orbit of that is basically GS G inverse, right? Such that G is in G. And this is basically nothing but the set of all distinct conjugates of S, right? We can use the term distinct because it is a set, so there is no repetition. So the order of the orbit is nothing but the number of distinct conjugates of S, or the number of conjugates of S, right? But we know that the order of the orbit is obviously equal to the stabilizer of this set S, right? So yeah, we cannot use the term S here anymore. So let me change the index here. Okay, let this be P. Let this be A. So A. Clear? So the stabilizer of A. But what is the stabilizer of? We have just proved that this is nothing but the normalizer, right? This is the normalizer. Clear? Other part is fairly trivial, because The normalizer of a singleton set S is nothing but the centralizer of S. Right? So this applied to this very set of statements will prove the second part of the proposition. Right? Let us come to the next proposition. I should say the next theorem, which is of high importance, extreme importance, which is the class equation. So it's another counting theorem. Okay. So theorem, and this is called the class equation. Called the class equation. Okay. So let G be a finite group. Let G be a finite group. Now, obviously, we can speak of counting the elements in G if and only if it's a finite group, right? So let G be a finite. I do not remember if I had explained or if I had said that G must be a finite group to have this relation, that cardinality of G is same as the order of some element A times its stabilizer. But it should be very evident to you. So let G be a finite group and G1, G2, GR till GR be the representatives of the distinct conjugacy classes of G. Okay, not contained in the center of G. Then G can be represented as the cardinality of G can be represented as the cardinality of ZG, that is the center of it, plus summation over the index of all the centralizers of the element Gi is equals to 1. Representation of the distinct conjugacy classes basically means that these are those elements in G which are not in the center of G and which have distinct conjugacy classes. So that is the very trivial meaning of it. How do we prove this? The proof is fairly simple because we know that the elements in the center of G have singleton conjugacy classes, so their orders are all 1, right? So if we can write it like this. Let's say if say ZG, so the proof, right? So if ZG contains of the elements say 1, Z2, Z3, so Z0, Z1 is basically considered to be 1. Yeah? So till say some ZR, have I used a term R? Yeah. So let this be Zm, and let K1, K2 till Kr be the distinct conjugacy classes corresponding to each Gi, right? Or else just G1, G2 till Gr. So Ki is the conjugacy class of Gi. Clear? Then the conjugacy classes of G are basically singleton sets of all these elements, right? So 1, Z1, Z2, so on till ZR, plus and each of these conjugacy classes. So K1, K2 till Kr. Okay, this is Zm. Now the conjugacy classes are nothing but orbits of elements, and we know orbits are basically equivalence classes. So every orbit partitions the group G, right? The orbit partitions the set A, but here set A is only the group G. So so other way of speaking that the conjugacy classes in a group G partitions it. So if so the summation of or the disjoint union of all these elements, all these sets give out the whole of G. So therefore G can be written as, so it can be written as the cardinality of 1 plus cardinality of the set Z1, so on till the cardinality of the set Zm plus the cardinality of K1 plus the cardinality of K2 and so on till Kr, right? But this whole thing is nothing but the cardinality of ZG, right? Because so 1 is in ZG, Z1 is in ZG, till Zm is in ZG, right? And so the number of elements here are exactly the number of elements in ZG. And we know that the order of a conjugacy class is nothing but uh, the index of the centralizer of its representative in G. So this is summation over I is equals to 1 to R, the index of the centralizer of the representative of each of this. Just the previous proposition was this only, right? This is centralizer of Gi, right? And this is the class equation which you wanted to prove. Clear? Okay. Let us consider a few examples. Example number 1. What happens if G is abelian? What happens if G is abelian? So if G is abelian, then ZG is equals to G, right? ZG is equals to G. Now if ZG is equals to G, then this thing has no value. And every centralizer over all the elements GIs are obviously equal to ZG, right, by definition. Right? So in this case, G must be equal to ZG. Therefore, all conjugacy classes are of size 1. Therefore, if you represent G as summation of each individual conjugacy class, so it can be written as 1 plus 1 plus 1. Correct? Correct? Let us consider the concept of Q8. Okay? Obviously. Now, we know that the cyclic group generated by I is abelian, right? So we can say that the cyclic group generated by I, so this is a subgroup of the centralizer of I, and it is a subgroup of Q8, right? Now I is obviously not in the center of Q8 because I doesn't commute with J, I doesn't commute with K. And what is the order of I? The order of I is 4. The order of Q8 is 8. So what is the index of the centralizer of, sorry, what is the index of the subgroup I? So it's 2. So if it's 2, then it's obvious that the centralizer of the element I is nothing but the subgroup generated by I. Right? We had previously proved it also. What are the conjugates of I? So it's plus minus 1 and plus minus I, right? Right? Oh no, sorry. The conjugates of Q8 are I and minus I, yeah. Are I and minus I. You can write minus I as Ki K inverse. Right? Therefore, what are the conjugacy classes? Now remember that the center contains only the elements 1 and minus 1. Right? So the order of the center is 2. And as we have this set of statement for I, we can also have this set of statements for the cyclic group generated by J as well as for K. So this is having the index 2, this is having index 2, this is having index 2. So since the centralizer of I of the cyclic group generated by I is I itself, right? Centralizer of I is cyclic group generated by I, centralizer of J is the cyclic group generated by J, centralizer of K is the cyclic group generated by K. So the index of the centralizer of I is 2, index of centralizer of J is 2, index of centralizer of K is 2. So what is the class equation? So G can be, so cardinality of G can be written as, so the number of elements in ZG, right? So it's 2 plus the index of the centralizer of I, that is again 2, index of the centralizer of J again 2, and index of the centralizer of K again 2. This is the class equation of Q8. Clear? Exercise. Show that the class equation of D8 is same as Q8. So it's 2 plus 2 plus 2 plus 2. If I give a simple hint of it, then if you remember that the center contained only two elements, 1 and r squared, right? So this is from the set 1 r squared. Then frame this part. What are the possible centralizers? Okay, I'm giving more hints. So this index is from the centralizer r cube. This is from SR squared, and this is from SR cube. Then try this out. Okay. So the class equation comes up with a very important theorem which characterizes those groups which have prime power orders. Okay. Theorem. If P is a prime, if P is a prime and capital P is a group of order P to the small p to the power alpha, where alpha is greater than or equal to 1, then the center of P, that is this, is non-trivial. Non-trivial means that is the order of center of P is greater than 1. Trivial means it is only the identity subgroup, right? So it must have order 1. So we are saying that the center must be non-trivial. Okay. And the proof is fairly simple, because what do we have from the class equation? So this is basically equal to, okay, so we know that G can be written as center of G plus summation over I is equals to 1 to R, let's say, index of each centralizer. Say P small pi. Okay, where each small pi is a representative of the distinct conjugacy classes in G. Yeah, that is where P1, P2 till PR represents the distinct conjugacy classes of G. Obviously, they are not in the center and are not in the center. Are not in the center. Clear? Now, obviously, by definition, the each centralizer Gi is obviously not equal to P, right? Is not equal to P. Got it? But this implies that P must divide the centralizer of. So this must divide the index, right? CG. Yeah. Because what is the index? So the index is basically this by the centralizer, right? Right? This is the index. So P divides the order of G. Therefore, P obviously divides the index, right? Now, since P divides the order of G as well, so what does this imply? Or you can just speak of the fact that since this is a subgroup of P, so this must divide P. So if this must divide P, it also must be of some prime power. If it is of some prime power, then P must divide this as well. Since P divides G and P divides the index CGPI for all PIs in G outside the center, that implies P must divide the center as well from the class equation. Division holds on either side of equality, right? So P divides this, P divides all the elements in this, that means P must divide ZG as well. Therefore, P must divide ZG, the order of ZG. But that implies the order of ZG must be that. Otherwise, how can a prime divide this very element with this very number, right? Clear? Okay, let us move on to the last proof of this, which is a corollary of this theorem, and which is also again very highly important because it helps in characterizing the groups of order p prime squared. Okay, so corollary. Okay, so whatever corollary says, so if this group capital P has order p squared for some prime p, then P is abelian. Then P is abelian. That is, ZP must equal P. More precisely, if P is abelian and of order P squared, then we have the following, that P is isomorphic to ZP squared or ZP cross ZP. Clear? Let's go to the proof of this. Clear? Suppose you have a group, say G, such that the order of G is 9. So then we can directly say that G must be abelian, right? Because G is of the order 3 squared. And if G is abelian, then, and G, so since G has order 9, so G can be written as, so G is isomorphic to Z3 squared or Z9 or Z3 cross Z3. Clear? Yeah, let's come to the proof of it. Now, obviously, since P is a group of order prime power, so the center is obviously non-trivial. Since center of G is greater than 1, then what are the possible orders of the center of G? Then center of G can either be of power P or of order P squared, right? But that implies that we know that the center of G is a normal subgroup of G, so we can obviously define the so the quotient group G mod ZG. Then what are the number of elements in G mod ZG? So it's either P or 1, right? Because G has the cardinality or the order P squared. If the order of ZG is P, then the order of G mod ZG is P. If the order of ZG is P squared, then the cardinality of ZG is, then the order of G mod ZG is 1. Because the order of G mod ZG is nothing but the order of G divided by the order of ZG. Clear? And the reason behind this is again very simple to notice, because we know that the order of G can be written as the index of ZG in G times the order of ZG, right? But since ZG is normal in G, therefore the set of all left cosets of ZG, can be considered as a group which is G mod ZG itself. So the number of elements in G mod ZG, that is precisely the order of G mod ZG, is nothing but the index of ZG in G, right? So this is itself the G mod ZG. You can think of it like this, yeah, correct? Okay. So we have this, right? Now, so if the order of G mod ZG is P, then G mod ZG is a cyclic group. Again, if G mod ZG is 1, then it's again a cyclic group. So we have G mod ZG. We were using the term P, right? Yeah. So just replace G with P in these statements. Okay. So we have P mod ZP is cyclic. And we have a very important proposition related to centers. We have not discussed about that. We won't even prove that yet. You can consider that to be a fact right now. So if the quotient group P mod ZP is cyclic, then that implies P is abelian. So the proposition is something of this sort, that if G mod ZG is cyclic, then G is abelian for any arbitrary group G. Clear? Then P is abelian. Okay. Now, if P has an element of order P squared, Then from the study of order of an element and order of a group, order of a cyclic group, these things we have covered in some previous lecture. Then P becomes cyclic. Then P is cyclic, right? And if P is cyclic, P is abelian, right? This is pretty easy to notice. Okay. So assume that every non-identity element of P has order small p. Okay. Now let X be a non-identity element from P, and let Y again be a non-identity element from P which is not equal to X. Clear? Then obviously the order of the subgroup generated by X and Y, this is greater than the order of the subgroup generated by X, which is very trivial to notice, right? And the order of the subgroup generated by X has the order P because X has order P. X is a non-identity element of capital, right? Now since X and Y both has order P, therefore the order of this must be equal to P squared because this is a subgroup of G, right? This is a subgroup of G. So this must has order P squared, right? So if this order P squared, we can define the cyclic group generated by X cross the cyclic group generated by Y to be isomorphic to ZP cross ZP, right? Because we know that a cyclic group of order n is isomorphic to Zn. Z mod nz, this set, let me just briefly write it down. We know that if you have a cyclic group, say X, suppose this is order n, then this cyclic group is isomorphic to Zn. Z mod nz, right? And Z mod nz is isomorphic to Zn. Zn is the set of elements 0 to n minus 1 with addition modulo n, and Z mod nz exactly contains those elements. Just we consider the elements in Z mod nz as residue classes of the integers, right? But they are actually the same elements and they have the same operation. So this is trivially isomorphic. ZP cross ZP, right? So the cyclic group generated by X is isomorphic to ZP, Y is isomorphic to ZP, so this is isomorphic to ZP cross ZP. So further notice that if you map X to the power A and Y to the power B, this element to X A Y B, this is an element in P. This is an element in P, and this is an element in cyclic group generated by X cross cyclic group generated by Y. Then this mapping, suppose it's phi, then phi is an isomorphism onto, clear? That completes the, okay. So that is all for this lecture. In the next lecture we will be trying to discuss the left regular action of G on itself, or the left multiplication action of G on itself, okay, which will eventually give us the important theorem of Cayley's theorem. Okay, so meet you guys in the next lecture.